Hello everyone, we are now going to begin our lecture on chapter 2, which is on set theory. Now we'll start with the first section of chapter 2, which talks about set concepts. So we will learn what a set is and how to define sets, as well as the different terminologies, different symbols we use to describe sets. Now, sets are a very important part of life, especially in science and mathematics. We like to group objects that fit the same characteristics into classes or into groups, and we call them a set of items or set of objects which match specific characteristics by which we classify them. In science, we classify a species of different living things into different groups, right? Likewise, in mathematics too, we group numbers of that fit certain type of characteristic, and not just in math and science, but all around us, we can classify objects into different sets and work with them. It just makes things a lot more manageable and easy to work with. So we're going to go into the details of that in the next few slides of this section of the chapter. So this is what we are going to learn in this particular section on set concepts. We will learn to understand the use of description, roster form, and set builder notation to indicate a set. And then we'll understand the fundamental set concepts, including finite sets, infinite sets, equal sets, equivalent sets, and the cardinal number of set, as well as null or empty set and universal set. So there's a lot of terminology we have to learn about different kinds of sets in this particular section. All right. So let's start with a definition of what a set is. A set is a collection of objects which are called elements or members of the set. So it is a group of objects, and we call the individual objects in a set the elements, or we can also refer to them as members of the set. Now, there are different ways, actually, there are three different ways by which we can describe a set, well, indicate a set. And the first one is a description. So we can define a set using a description. That means in a sentence, all right, that uh, a set of all capitals of US states, all right, or all states in the US. So it is a wordy way of indicating or describing a set. By the description method in mathematics, we rarely use wordy language to define something. We try to describe things in a notation form. So the second method is the roster form, which is also more or less, it's less wordier than the description method, but still contains all individual elements. We name the individual elements in the roster form of definition of a set. But finally we have what's called the set builder notation, which is a more concise way of indicating a set. Now, sets can either be well-defined sets or ambiguous, not so well-defined set. So a well-defined set is one where the contents can be clearly determined. So the elements of the contents are explicit and are known. that would be a well-defined set. For example, the set of US presidents is a well-defined set because its contents, the presidents, can be named. The set of the days of the week is a well-defined set because we all know the days of the week, Monday, Tuesday, Wednesday, and so on, all the way to Sunday, to be the elements of the set. In that case, it is regarded as a well-defined set. Here's another example of a well-defined set. It says here, write a description of the set containing the elements January, February, March, April, May, June, July, August, September, October, November, and December. So here in this example, they are remember, there were three ways by which we could express a set. One was the description method. So here we will write in a sentence with a full sentence, including the elements of the set, and describe the specific set. All right. So let's go on to the next slide to see how they are using or how they are defining or expressing the set using the description method. So using the description method, we can just write in a sentence, the set is the months of the year. Now, we do not need to specify the exact names of the months. We can just write it as the set is the months of the year because it's a well-defined set, and the months of the year are pretty much known to everyone, right? So we can just leave it as a sentence in this form saying the set is the months of the year. Now the second method of expressing a set is called the roster form, and in this roster form we list the elements of a set inside a pair of braces, curly brackets, or sometimes also called parentheses, and this is called the roster form where we use these brackets or braces, and inside the braces we list the different elements of our set. So for the previous example where we said the set of the months of the year, which we expressed in description form, we could also express the same in roster form by using these braces, but inside the braces we would have to list all the months of the year. So January, February, March. So we would have to specifically spell out the different months of the year all the way to December, and then close it with another curly bracket. All right. So this is the roster form of expressing a set. Now, another example of that is we could just use the roster form to describe a set where the elements are 1, 2, and 3. This is the notation for the set whose elements are 1, 2, and 3. So 1, 2, 3 and 1, 2, 3. You see here there are two different kinds of brackets. All right. This is a round bracket. This is a square bracket. These are not sets because parentheses and brackets do not indicate a set. They have a different meaning in the world of mathematics, but when we are expressing a set, we always use these curly braces or brackets. Okay. Now there are specific conventions used in math to name sets. So let's go over those. First of all, sets are generally named with capital letters. For example, if we want to define natural numbers are whole numbers starting from 1. All right, but they are whole numbers. They don't include fractions. So to define natural numbers, we write it in in a description form first. It says the set of natural numbers or counting numbers is n. All right, so we name it as n, an uppercase n in capital letter, and then we can write it in roster form, or we can also use the description form. All right, so over here we have it shown in roster form, where capital N is equal to, then within these braces we have listed these numbers, the natural numbers starting from 1 to 1 comma 2 comma. You have to put in the commas to separate the elements, and then these three dots are also called ellipses, right? So let me write that. These are called ellipses, and the ellipses tell us that this pattern continues, right? So the set of natural numbers or counting numbers is n, can be represented as n equals, and then you have to use these curly braces and then list the different elements, up to a few of them separated by commas, and then you can use the dot dot dot, because n will keep going, natural numbers keep going and going all the way to very large numbers. They're not possible to list all of them on a paper, so we just represent them with these three dots. All right. So let's go through this example here. It says express the following in roster form, and they have described the set. So it says set A is the set of natural numbers less than 6. So how would we go about writing this in roster form? So first it says it has given a name to the set. So we are going to write a capital A on the left, then put an equal sign, and then we are going to list the elements of the set, but we first have to put or write a brace, open brace here, and then we will list the numbers 1, 2, 3, 4, 5, and each of these numbers should be separated by a comma. And then based on the description of the set, we will stop at 5, because it says the set are natural numbers less than 6. So 6 is not included. We stop at 1 less than 6, and then we close the brackets, or close the braces, so to speak. All right, so the solution they've given us is A equals, and then our braces open, 1 comma 2 comma 3 comma 4 comma 5. They stop at 5 too, and close the braces. So that is the roster form of defining or describing set A is the set of natural numbers less than 6. Right? Another example here to express a set in roster form. It says set B is the set of natural numbers less than or equal to 5. So that means the set will contain elements starting from 1 all the way up to 45, all right, because it says here less than or equal to, so we have to include 45 in our set. So the way we are going to write that in roster notation of sets is B, the capital B, equals, then your braces start, and then you start from 1 comma 2 comma 3, and then after a few values you just use your ellipses, and then the last number is a 45. All right, and close your braces. So let's see how they've worked it out here for the solution. So same thing here, B, capital B equals, then the braces start, 1 comma 2 3 4, and then 3 dots, and of course we have to separate the dots also with a comma, which we didn't do here. All right, so let's put the commas uh, between the ellipses, and or rather between the numbers around the ellipses is what I meant to say. And that defines this set. We do not have to write each and every number. It's a well-defined set. We know all the numbers between 1 and 45 inclusive, so we can just write a few and then skip the rest and end the set uh, with the last value in the set, which is a 45. One more example here. The set P is the set of planets in Earth's solar system. So essentially, the set contains elements which are names of the different planets in the solar system. So the way they have written that is P equals, again, use a capital P to name your set, and then within brackets or within these braces, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. All right, these are the individual names of the planets. You have to list them all. Now we will go over some symbols and some notations we use typically in set theory. The first one is the symbol here, which is like a fancy E, so to speak. Red is an element of. So this symbol here, which looks like an E, kind of a rounded E, implies is an element of. It is used to indicate the membership in a set. All right, so there's another one which is the same E but crossed out diagonally. All right, the symbol E with the diagonal cross out means it is not an element of. All right, so we will use these two symbols to denote whether a certain element is a part of a set or is not a part of a set. Now, what the symbols that we learned previously, if something belongs to a set or does not belong to a set, the symbols that we will be using is really meant to be used in the set builder notation. So we will learn more about how to represent sets in set builder notation. What is a set builder notation? It is nothing but a formal statement that describes the members of a set, and it is written between the braces as well. All right, just like for the roster form, we used braces. Similarly, to represent a set in set builder form, we will build the set notation around the braces. Okay. Now, a variable may represent any one of the members of the set. So let's say we have a set which is in roster form, which says A equals, and then 1, 2, 3, 4. All right, let's say this is the set we have. We can represent these elements of the set with a variable, and that's exactly what we are going to do when we build something in set notation. Right, we are going to represent these elements of the set as X. So let's go on to the next slide to see how we go about that. We are now going to use this example and learn through this how to use the set builder notation. So the set given to us is B equals, and then within braces we have the numbers 1 through 5, and we have to describe this set using the set builder notation. Now recall that we learned previously, or we were told previously, that in the set builder notation we use the same pair of braces that we do for the roster form, And then there were a couple of symbols that we learned. One is this E-shaped symbol, which means or which implies that some value is an element of. So it reads as is an element of, or is a member of, element or member of. Okay, and then we have another symbol which indicates just the opposite, which is this E-shaped symbol but crossed out, and that means is not a member of. All right, let's separate this. Is not a member of, or is not an element of, or does not belong, so to speak. And we will use one other symbol, which is this vertical bar, and that vertical bar reads as such as. Reads such as. All right, so let me just surround this in brackets. Just give me a second, 1 second. Okay, so this vertical bar implies such as, and we are going to use a variable, x maybe. We can use any variable, but we will use x to define any value within the set. All right, so these are the symbols, notations we are going to use. But let's look at the values given to us in the sets. In the set B, we have values starting from 1, and these all seem to be natural numbers. It starts from 1. If we had a 0 here, then it wouldn't be a part of a set of natural numbers. It would be a different set of numbers, but this starts at 1, but it ends at 5. It doesn't go beyond 5. So it contains 5 elements from 1 through 5. So how do we define that using the set builder notation? We are going to start with B, all right, the name of the set, and then the equal sign, and then we open our brace, and then we write our x variable, and this variable will represent any of these numbers. But we said two things, recall. We said this is a set of natural numbers, and the numbers don't go above 6. Above 5. All right, it's just from 1 through 5 inclusive. So we are writing x to represent these numbers, and then that is followed by this vertical bar which reads such as. The same vertical bar. Just a second, let me pull up the pointer here. So this vertical bar reads such as. So we are saying x is an element such that, again, x is a member. We denote that with this symbol, E-shaped symbol, is a member of n, and n is used to denote natural numbers. All right, n is used to, this uppercase n is used to denote natural numbers. We learned that previously. But it's not just the set of all natural numbers. If you leave it like that, then it would mean that this set contains elements which are all natural numbers. That's not the case. The elements stop at 5, correct? So we have to kind of go on with this to describe that. So we have to say and x is less than 6, and then close the brackets. Now we could either write x less than 6, or you could say x less or equal to 5 as well. That would also be correct. All right, so let's read what we've written out. We read it as B is a set where B is a set of variables, set of values x, such that x is an element or a member of a natural set, and x is a value less than 6. Now the fact that we said it belongs to a natural number set means it should start with a 1. All right. So in the next slide, let's see how they worked out the same questions. So here is how the book has given the solution for that problem. Here it's b equals, and then you have to use the braces, so open brace, and then x such that x is a member of n, or s belongs to n meaning the set of natural numbers, and x less than 6. And then the alternate way is to say b equals, again, x such that x belongs to a set of natural numbers and x less or equal to 5. So the description of this set notation is the set of all x such that x is a natural number and x is less than 6. Let's look at this example here. Here we have been given a set notation and we have to write it in roster form. All right. So let's read this set notation first. It says A equals, and then within the braces you have x such that x is a natural number and x is a value between 2 inclusive and 8 exclusive. Now, what does inclusive and exclusive mean? When you have the symbol less or equal to, when there's an equal to included in the inequality, that means 2, this number here 2, is included in the set. However, on the other side, x less than 8, it just has less than, it doesn't have equal to. That means 8 is not included in the set. All right. So when we have to write this in roster form, we start with A equals, and then open braces. So what numbers do we put as elements in the set? It would be 2. All right, 2 is included because of the less or equal to. 2, 3, 4, 5, 6, and 7. And we stop at 7. 8 is not included in the set because there's no equal to sign with the less than. All right, so let's see what the solution is here. So solution is A equals, and then within braces, just what we wrote here, 2, 3, 4, 5, 6, 7. All right. Now let's talk about finite set. A finite set is one which contains either no elements or the total number of elements in the set is some natural number. All right. So it should meet two conditions in order for a set to be a finite set. First, one of them is that it may not have any elements, it may be an empty set, or if it has elements in it, the total number of elements in the set is a natural number. So here's an example. It says here set B has these elements 2, 4, 6, 8, 10 is a finite set because it has elements in it, but the number of elements, that means how many elements do we have in this set? 5, correct? So the number of elements in the set is 5 and 5 is a natural number. All right? Likewise, an infinite set is one which is not finite. The set of counting numbers is an example of an infinite set. So counting numbers are separate from natural numbers. Remember, for a set to be a finite, the total number of elements would be uh, should be a natural number, correct? A counting number, on the other hand, starts from zero, and it can you can keep counting to higher and higher and higher numbers, right? It can go to infinity. If we have a set of counting numbers, it's called infinite. It's an infinite set. Next is equal sets. What is an equal set? Set A is equal to set B, symbolized by A equals B, if and only if set A and set B contain exactly the same elements. Now, the elements may not be arranged in the same order, but if both A and B have exactly the same elements as well as the same number of elements, then they are considered to be equal sets. So here's an example. We have two sets in roster form here. First one is 1, 2, and 3. The other one is 3, 1, and 2. All the elements of set 1 are also there in set 2, correct? So that makes both the sets equal. Now, another term that we come across in set theory is called the cardinal number. The cardinal number of set A, symbolized as n, and then within brackets we have A, is the number of elements in set A. So when we have to denote the number of elements in a particular set, we call that the cardinal number, and this is how it's symbolized. Lowercase n followed by an uppercase A within brackets. All right. So here's an example. We have A equals, so just a second. Let me pull up all the, so we have here A equals 1, 2, and 3, and B has the elements England, Brazil, and Japan. Both the number of elements in both is 3, correct? 3 elements in A, 3 elements in B. So they have cardinal number B. So n sub A, or the cardinal number of set A, is a 3, and the cardinal number of set B is also a 3. Now there's another terminology that we should be familiar with. It's called equivalent sets. What makes two sets equivalent? Set A is equivalent to set B if and only if n, so the cardinal number of A is the same as the cardinal number of B. Then they are called equivalent sets. So there's a difference between equal sets that we learned before and equivalent sets. In equal sets, two sets have the exact same elements, the same number of elements, and the values of the elements. In equivalent sets, the values may be different, but the size, the cardinal number, or the number of elements in two sets are the same. All right, so here's an example. Set D has elements A, B, and C. E has elements apple, orange, and pear. And as we can see, N of D is 3, and N of E is also 3. So that makes the two equivalent sets. All right. Now diving into the difference between equivalent sets and equal sets. Equivalent sets have to do with the size or the number of elements in the set. All right. On the other hand, equal sets have to do with the values of the elements itself, all right? Not the size, but well, it has to do with the size as well, but it also looks at the values of the set, values of the sets. Okay, so let's look at what this says. Any sets that are equal must also be equivalent. All right, so equal sets not only have to have the same size, but they also have to have the exact same values, right? Not all sets that are equivalent are equal. So equivalent sets may not be equal sets. That means the two sets may have the same size, but the values could be completely different, right? For example, here we have two sets, D equals A, B, and C, and E equals apple, orange, and pear. So we see the number of elements in D is 3. Number of elements in E is 3 as well. That makes the two equivalent sets. However, they are not equal sets because the values are completely different. The values of the elements are completely different in the sets. So as it says here, to wrap up, the cardinal number of each set here for D and E is 3. So that makes both of them an equivalent set. So set A is equivalent to set B, but the sets are not equal, right? Now, one property that sets can assume is called the one-to-one correspondence. So we will go through a definition of what one-to-one correspondence is, and then we will look into an example to understand how it works. So here it says set A and set B can be placed in one-to-one correspondence if every element of set A can be matched with exactly one element of set B, and every element of set B can be matched with exactly one element of set A. All right. So again, A and B will have elements which will not be the same, but they will map to each element in set A will map to exactly one element in set B, and each element in set B will map to one exactly and only one element in set A. All right. So let's look into an example because this can be better explained with an example. Here's an example of one-to-one correspondence. It says, consider set S states of the US and set C state capitals. All right, so if we pull up the first set, Here we have S equals, that means the states of the US. And they have 4 states here: North Carolina, Georgia, South Carolina, and Florida. And then the capitals are, which is set C, Columbia, Raleigh, Tallahassee, and Atlanta. So we see there's a relationship between the elements of set S and the elements of set C. All right, so the first is the set of states, then we have this capitals, but each element of state S should map to exactly one element in state C for it to become a one-to-one correspondence. All right, but for one-to-one correspondence, it has to go both ways. So over here, North Carolina's capital is Raleigh, right? North Carolina's capital is not Columbia, not Tallahassee, not Atlanta. North Carolina maps to only one value in set C, and that's Raleigh. So we have a one-to-one correspondence. Let's go the other way around. Raleigh is mapping to only one element in set S, correct? Raleigh has nothing to do with the state of Georgia, doesn't have anything to do with South Carolina or Florida as far as capitals are concerned. All right? It's a one-way mapping. North Carolina maps to Raleigh and Raleigh maps to North Carolina. Likewise, Georgia's capital is Atlanta, and Atlanta is the capital of Georgia. Again, this is a two-way correspondence, but only to one element in the set. All right, so this maps like this: Atlanta, and Atlanta maps to Georgia. Likewise, South Carolina and Columbia map with each other. They are related. Columbia is the capital of South Carolina, and South Carolina state, capital is Columbia. And then Florida, Tallahassee, and Tallahassee, Florida. So these are all one-to-one correspondence where one element in state in the set S maps with one element in the set C and vice versa. Right? So two different one-to-one correspondence for set S and C are. Let's go on to the next slide to see what they are. So they told us that there are two mappings possible, and one, of course, doesn't make sense, as you will see here. Just a second. All right, here they are coming up with a forced mapping where North Carolina is mapped to Columbia. So Columbia is not a capital of North Carolina, but we can force something. All right, we can forget that these are really capitals, and we may just link them, the first to the first, the second to the second, third to the third, and fourth to the fourth. All right, that's one way of mapping, although in this particular case it doesn't make much sense. All right, but in some situations, or there would be many examples when we are looking at ordered pairs in a linear equation, the ordered pairs, they would be matched or mapped by position. First element mapped to first element of the second set, and so on. All right. And the other one is what we just discussed in the previous slide: match the states with the capitals. So North Carolina to Raleigh, Georgia to Atlanta, right? And then South Carolina to Columbia, and finally Florida to Tallahassee. So we make this more meaningful in this case. This one is not as meaningful. We just matched the positions of each element. So yes, two different mappings are possible, one by position, and one is more meaningful where we match the states with their respective capitals. Null or empty set. The set that contains no elements is called the empty set or null set and is symbolized by the braces, an empty pair of braces, or this value which represents null. All right. So we could represent empty or null set in two ways. We can symbolize it in two ways. One is just have a pair of braces with nothing in between the braces, or we use this special symbol, which is an O with a diagonal bar crossed out sign. It represents null in many cases. Now, a few things about the null and empty set. The null sets are not really empty sets. All right, that this null is not the empty set because null is considered to be a value. It is a particular element in a set which is null. So this set contains the element null and has a cardinality of 1. So it has a size, it has a dimension of 1 here. On the other hand, the set 0 is also not the empty set because it contains the element 0. It has a cardinality of 1. All right. So null, when you see this null symbol, that means it is not necessarily an empty set. It has a cardinality, it has a size, it has a dimension of 1, and 0, which is a number, also is not considered to be an empty set because it has a size. There's still one element in the set. Now, one last type of set that we must know about is called the universal set. The universal set, symbolized by U, contains all of the elements for any specific discussion. So they represent all the elements that can go into a particular set from which the elements of a set can be obtained. For example, the states of the United States. All right. So let's say we are talking about, or we are creating a set for the states of the United States. The universal set for that would be all the 50 states of the country. All right, that would be considered a universal set, but we could just use 4 or 5 of them from the universal set to create a subset. But the universal set would have all elements in it. All right, if we are talking about states of the US, then it would have all the 50 states, and so on. All right. So over here it says when the universal set is given, only the elements in the universal set may be considered when working with the problem. So that means that, for example, on the particular example of states, uh, the values that the set can take would be one of the values from the universal set, which would be the states of the country. All right. So looking at an example of an universal set, we have here a universe of set defined as U equals the numbers 1, 2, 3, 4 up to 10. All right. If this is the definition of the universal set, then only the natural numbers 1 through 10 may be used in that problem. All right. So if we are to create smaller subsets from the set of universe, from this universal set, or from this universe of values, then the numbers in the subsets better be values between 1 and 10, right? So it all depends on how the universe is defined.